So today's lecture is going to be about these problems I'll call prophets and secretaries, or that's the name that that's popularly used. So the problem is going to be kind of similar in spirit to the previous lecture, but there are going to be some new aspects to it, and then so I'll emphasize those. So let me give you the sort of main problem. By the way, so I have some written lecture notes. So there are some LaTeX lecture notes, and they should be available on the Gather Town and stuff like this. And stop me. This is more of a I don't have slides, so we can go in whichever direction we want. So there is a lot of flexibility today. Okay, so let me tell you the basic problem. And
Anupam, sorry. Maybe if somebody didn't see, so in the chat there's the link for the whiteboard if you want to access it directly, and you can scroll it. Yeah, sorry for an interruption.
And yeah, you can. The good thing with the whiteboard is you can go back and forth if you need to. Good. So here's the general problem, and this is often called the prophet problem. And so the problem is the following: there are a bunch of random variables, x1, x2, up to xn. You know their distributions, just like last lecture. You don't know their actual values. And it's now an online problem. So what you're going to be, what's going to happen is you're going to be shown the value of x1. So in some sense, the box is going to be open for you. And you can decide to either take the value of, you take the value that you see, or you say, no, I don't want this value. And then you move on and you can never come back to it. So you see x1 and then you accept or reject. And then you see x2, accept or reject, and so on and so forth until you see xn. And you know their distributions, of course. Okay. And so what you would like to do is, of course, you can define xmax to be just the max of all these random variables. And you ideally would like to get a strategy which gives you expected xmax value. This is the optimum in some sense. This is what somebody who can see the future, who knows exactly what's going to happen in the future can get, because it's just picking a max of n numbers, right? So this is known as, people think of this as, this is what a prophet would get. And what you want is you want an algorithm. So you would like an algorithm whose expected value is at least, let's say, expected x max over some constant, let's say. And such an inequality is known as a prophet inequality. And this, stuff has been studied for quite some time in the in probability theory, in particular in optional stopping time theory. So what we are interested in is, of course, these same issues, but we are also interested in maybe sort of algorithmic problems. We are interested in generalizations of these questions. And so this is what I'm going to talk about in the prophets part of the talk. The secretaries will come later, and maybe we'll see how much secretaries we can do. But good. So this is the question clear? You see x1, you have to accept or reject. You see x2, you have to accept or reject. You can never go back. And you want to get a strategy which gives you some result like this. And some of you might be thinking, hey, this is very similar to the best box problem that we chose last time. In the best box problem, you could open the boxes one by one. You could open at most B boxes. Now, I'm not placing any restrictions on the number of boxes that you can open. And indeed, you do know the distributions beforehand. So all the distributions are known. Good. We'll come back to this question, though. How much do we know about the distributions? Okay. So you could say this is very similar to the best box problem. In the best box problem, of course, I told you can open as many boxes as you want. And then once so up to B boxes, and then you go and pick the best of the results that you've seen. And sneakily, you'll remember also that the algorithm I gave you was doing something smarter, was actually when it saw an item, it decided to accept or reject right there. So in fact, if you think about it, you can use that algorithm to solve this problem. Okay. And the connections will become clearer as we go along. But for the moment, if you don't remember last lecture, don't worry about it. Let's just look at this problem from the start. So in order to get a result something like this, this is a very beautiful result from, I think it's from the 90s. Actually, the result is very old. The result is from the 60s, but there's a very nice proof from the 90s, which says that you can actually get expected alg is at least expected xmax over 2. Okay, and this is this factor of 2 is tight. Okay, good. You can't do anything better in general. So what I'm going to do is I'm going to give you 2 proofs, and both these proofs are going to show you something sort of interesting about. Actually, maybe even 3 proofs. We'll see. Okay, so let's do proof 1. And proof 1 is by Esther Samuel Kahn, and she gave this sort of lovely proof. She said, okay, x max is a random variable. It takes on some value, some probabilities, right? So look at the median of this random variable. So let tau be the median of x max. And just for the moment, imagine that the distributions are continuous. So it'll make my life slightly easier. So what does the median mean? So that the probability that x max is greater than or equal to tau, and the probability that x max is less than or equal to tau is at least 1/2, let's say. Okay, the median. And you can think of this as exactly being 1/2, if it's a continuous distribution, no atoms and stuff like this. Okay, so just set this, look at this threshold. Since you know the distribution of all the x's, you know the distribution of x max. And computationally, you can ask, oh, how, what's the computational model and stuff like this. But like information theoretically, you know exactly what tau is. And your algorithm now is pick the first item bigger than tau. This is your algorithm. It's very simple, very clean algorithm. And I'm going to claim that this algorithm gets value at least x max over 2 expectation. Okay. The algorithm clear, right? It's the median. Okay. So here's the thing. Let's look at opt. So by the way, I'll get tired of writing expected x max, so I'm just going to call this opt. Okay. So what is opt? Now opt, let me give an upper bound on opt, and then I'll give a lower bound on my algorithm, and so we'll put these two together. Okay. So opt is at most tau plus, so maybe I'll say expected opt or something like this, plus the expectation of opt minus tau, the positive part of that. Okay. Fair enough. And this is at most tau plus expectation sum over I going from 1 to n of xi minus tau, positive part of that. Remember, opt is the max. I've kind of replaced the max by the sum. Sneaky, but valid. Okay, good. And now let's look at expected alg. So expected alg is, well, I'll get tau as long as the x max is bigger than tau. This much I'll get for sure. Okay. Plus, and now let's look at items from 1 through n. I'm going to get the value of xi minus tau, positive part, if I actually get to pick this guy. that all previous guys were less than tau. Okay. So I'm just kind of breaking up the money that I'm getting into two parts. I'm saying, look, there's some chance that I'll be bigger than tau. I mean, basically, I'll get money only when I'm bigger than tau, right? So I take tau of that money and put it in this first part. And then I take the rest and I put it in this part. And I'm just summing it up in two different ways. Okay? Good. So this is bigger than tau times, what is this probability? Remember, 1/2 plus, and now let's look at this xi minus tau, the positive part of that. And let's look at this probability. So all previous, so when I say all previous is less than tau, I basically mean x1, x2 up to xi minus 1 are less than tau, right? This is greater than equal to the probability that all x1, x2 up to xn are less than tau. Because here, I just want the first I minus 1 people to be less than tau. And here I want all people to be less than tau. Okay? So this is probability x max is, sorry. Fair enough. And this is 1/2. Oh, maybe I should have put expectations everywhere, right? I've been sloppy. So this is really 1/2 times tau plus sum over expectations of xi minus tau, positive part, which is the same as this, which is 1/2, which is at least 1/2 of opt.
Anupam?
Yep.
I got lost when you said you're taking expectations, which is correct, but I don't know if one should be doing like the law of total probability there, or like conditioning on these positive part random variables.
Good. So that's a very valid point. And in fact, what you should be doing is you should be looking at this whole thing as the, so what I've done is I've used independence sneakily somewhere out there. Right? And I'm saying, look, I'm really looking at the xi minus tau, the positive part, conditioned on all previous less than tau. But I'm saying, oh, everything's independent. So thank you for catching me out there. It's a very important point. So this step, when I took expectations, I was I was doing two things at the same time. I should have taken expectation of this whole expression, and then taken and then used independence. But it is doing the right thing. Okay. Maybe I'll it's a beautiful proof. It's one of these proofs that like you see it and you're like, wow, how did they come up with this thing? And maybe I can tell you one little thing about how I think they came up, how Samuel Kahn, she came up with this thing. Is look, here's the idea, and this is an idea which will resonate from previous lectures as well. I want to make sure that I reach every item with reasonable probability. And I want to make sure that I pick every item with reasonable probability. So this part is making sure that previous items don't block me. And this part is making sure that I reach, there's a reasonable chance that I'm getting value. This proof is a little mysterious, frankly. It's slick, and like all slick proofs, it worries me a little bit. So let me give you a different proof. Okay. Let me go on to the next slide. Let me give you a different proof. And if there's one thing that you'll get out of this whole thing, is that you'll realize that I like reducing everything to linear programs. If I can write a linear program and I can argue about it, I'm a very happy person. Okay? So now this is where it's going to come. And okay, so here's an LP-based proof. And this is, essentially this is this very nice paper of Shuchi Chawla and others. And good. Okay. So here's the deal. Okay. And more or less, here's what I'm going to do. I'm going to say, suppose, just hypothetically speaking, suppose I knew the probability with which this is the probability that xi is the maximum. I take I have these random variables x1, x2 up to xn, and I'm just drawing from these. And this is my experiment, and I'm just looking at the probability that the ith guy is the maximum. Okay. So what do I know about this? I know that the summation of pi is equal to 1. Somebody's got to be the maximum. Let's say there are no ties and stuff like this. And those things only confuse the matter. Okay. So now I can ask the question that good. So can I give an upper bound on how much value xi can give if there's a pi probability of it being the maximum? Okay. So what is xi? Xi takes on certain values with certain probability. Okay. Actually, yeah. And now I want to say that suppose I look at, what do I look at? So I look at a point such that this probability is equal to pi. And I look at this conditional expectation. So I look at the expectation of xi conditioned on xi being bigger than this tau. Remember, this event is happening with probability pi. I want to claim that the value I can get from xi is at most this quantity. If I told you, look, here's a random variable, you can pick it with probability at most pi. How will you get the maximum value? When you say, oh, I look at all the highest value items, the highest values that xi can take, and look at their total probability, and if it becomes equal to pi, then that much value I can get. Does this make sense? So remember, what did I do? I said, look, you told me that the probability that I can pick xi with is pi. So I should pick xi for the highest pi probability. Yes, no, maybe. Okay. Let me go with this. So let's say that vi of pi is the expected value. Oh, is exactly this expected value. Okay. Where tau, what is tau? Tau is being chosen to be the choice. So it's, let's say, the choice such that the probability of xi is bigger than tau is actually equal to pi. So for every choice of probability, suppose I told you, well, you can choose xi always. Then the maximum value you can get is, well, the expectation of xi. And suppose I told you xi can be chosen with probability at most a half. You would like to choose xi only when it's taking on the half highest probability. So I want to say that opt is at most summation over pi times vi over pi. This is the probability with which I choose the ith item. And this is the conditional probability, the conditional value I get, such that pi sums up to 1, pi's are non-negative. I feel like I'm losing you guys.
I have a quick question.
Please.
So is pi the probability that xi is the maximum, or is like the probability that the player or the algorithm wants to pick xi?
Good. So it's the actual probability that xi is the maximum. We don't know this probability right now. So I'm assuming out here that suppose somebody told me these pi values.
Anupam,
Please.
this tau should depend on I, right?
Absolutely.
Like it cannot
So
be
maybe I
the
should
same
write it as
for.
pi.
Okay.
Absolutely. So this is exactly the probability that this is the distribution function, the density function of xi. Okay. So I want to claim that this is an upper bound on optimum. I want to say, look, if you told me the PIs, I'm going to choose I with the right probability. I'm going to choose I when it's only in the highest region. Okay.
And there is a max over the PIs there, right?
Is the max over the PIs, P1 up to Pn. Absolutely. Thank you. So I was imagining earlier that the PIs were told to me were the actual probabilities. But since I don't know these things, now I can say, look, just take the max over all P1 through Pn. That is a valid upper bound. And in fact, it turns out that this problem is a sort of a convex problem in the P vector. So you can actually solve this if you wanted to, if you were given the distributions of x1 through xn.
But what is the sum then after the max? So what do you sum about?
So it's summing over all the items 1 through n. So this is just saying, look at the ith item. It's the probability of the ith item being the max times the conditional value. Okay. Let me continue for a minute and then let me come back. Good. So I want to say this is an upper bound. And suppose I solve this convex program. I knew the values of p's. So then my algorithm is going to be at the ith item, pick it with probability pi over 2. I was told that, pi is the probability that ith is the maximum. Okay. If I don't want to just pick it out blindly with probability pi over 2, if xi is bigger than this tau I value, if it is large, pick it with this probability. Okay. Now I'm making a mistake. Sorry. Give me 1 sec. Yeah, good. Okay. So first of all, I solved this convex program. And if you don't want to think about solving this convex program, just imagine that, somebody came and told you the probabilities that the ith is going to be the maximum. And using these probabilities, you figured out these thresholds. You said, look, I'll figure out with what probability, what's the threshold such that if I pick above this threshold, I'll pick with probability pi. Okay, this is my threshold tau I. And this is the conditional value that I get above tau I. Okay, good. And now my algorithm is, when you see the ith item, pick it with probability. I'm doing a mistake. Half. If it is large, pick it with probability 1/2. So my expected value is, look at all my items. What is the probability that pick the ith item? And what's the expected value condition on picking it? This is just, the expectation computation. Okay. What do I want to do? I want to say probability that I'm not blocked, that I have not picked an item earlier, right? If I'm not blocked, I'm going to pick it with probability 1/2. If it is bigger than tau I. And then if it is bigger than tau I, then the conditional value I'll get is this much. Okay. And you'll see, these are similarities to the previous lecture as well. There's the same kind of analyses that are going on. Okay. And then let me just finish up the analysis. This is VI of PI as we defined above. This probability is PI as we defined above. This guy is 1/2 as before. And I just need to make sure that I reach every item with probability at least some value. But this is exactly why I rejected with probability 1/2. So in expectation, I'd be picking half an item. So the probability that I've already been blocked is at most 1/2 by Markov's inequality. Okay. So there's, eventually there's some calculation out here. And sadly, not sadly, but interestingly, the reason for some of these choices comes up from this calculation. So in fact, the way to solve this problem is to actually do the calculation and figure out what numbers you should set so that the calculation works out. Okay, and this gives the opt over 4, because you lost a half there and you lost a half there. Oh, sorry, you lost a half there. Yeah, that somehow didn't go over quite so cleanly as I'd hoped.
Anupam,
yeah, please.
2 questions. One, the solution to the convex programming, is it obvious that the P sub i's will be the probability that xi is the max? That's one question. And the other one is, this gives a totally different algorithm than the previous proof, right?
Right. So in fact, okay, so let me answer the first one. So the beauty of this is that any solution that you get is an upper bound on opt. And the answer you are getting is comparing to the objective function of the optimum. So you are getting only better. So if you solve this convex program and it gives you a higher value, you're only winning. So that's the good part.
It's not that those are the probabilities of.
So those are just some weirdo values. They might not even correspond to real probabilities of something happening, good. But at least they're an upper bound. And as for the second one, indeed, this is a very different algorithm. So this problem, there are so many different ways I can give you. Well, actually, I can give you 4 different ways of coming up with this 1/2. And they all generalize in different ways. So here is a variant of this problem, which actually Hiep had asked me last time, is so what if instead of picking one object, in the profit inequality, I said you are allowed to look at all the, you're allowed to look at a box and you can choose at most one item. You only want to choose the max. But suppose I tell you, oh, you can choose 100 items. So this is like a multiple choice thing. You can open up boxes and you can say yes 100 times to 100 different people. The previous proof, generalizing this is a little tricky. It can be generalized, but the proofs were given only recently. Suppose you were allowed to pick 100 items. Let me tell you the generalized algorithm. So the problem is there are n variables. You can say yes to 100 of them. And the algorithm is going to be solve this convex program. It'll give you some, it'll give you some values, PIs. From those PIs, you are going to infer the tau i's. And you're going to run this exact same algorithm. And the proof will go through exactly the same. So this one has an advantage of generalization, or easy generalization, I would almost say, like mechanical generalization. And in fact, at this point, I can say, look, not only does it generalize, you can actually, it actually can give you a better result. Why did we do this half? So let's go back and say, our algorithm said at the ith item, pick it with probability 1/2. Why did we choose this probability 1/2? Where does this half come in the rest of the proof? It's not there in the previous part because there's no, it plays no role. Where does this half come in? It comes in 2 places. Well, of course, it comes in because I have to take into account what the probability of rejection. It comes in because I used it in this not blocking probability. I said, look, I reject every item with probability 1/2. So the expected number of items I pick is only half. So the probability that I pick twice as much is at most 1/2. And that's this probability. But if I were picking 100 items, I don't have to say, oh, in expectation, I have picked 50 items. So the probability of picking 100 items, I don't have to use Markov. I can use something much smarter. I can use a Chernoff bond. So in fact, instead of shading it down by 1/2, and this is getting messy, but let me just write it down out here. For k items, shade down by 1 minus square root of log k over k. And use a Chernoff bond. Okay, I'm going a little fast out here. So if you didn't get this, don't worry too much about it. It's there in the notes, and play around with it. And send me mail if something seems wrong.
There's a question in the chat.
Are these algorithms from a word? Yes. So they're equivalent in some sense. So that's a very good point, Bernardo. Practice is a slippery subject, and it's not something that I can say something meaningfully about. Yeah. So I don't have a good answer to your question. What I do know is, yes, they're kind of equivalent from the worst case perspective. So good. So this algorithm was very nice from the from a sort of generalization perspective. If you want to pick 100 items, that's great. If you want to make sure that your items, you are allowed to pick 5 items of red color and 3 items of blue color and stuff like this, you can put those constraints down. Okay. So in general, if you've seen these things called matroids, you can put any matroid constraint down, and the proof becomes more complicated. But this convex program is still good with any matroid constraint. The proof is more sophisticated now. It's not just a Chernoff bond.
Anupam, I think you might have covered this, but that program is not necessarily an LP, right? Depending on the distributions of xi's.
Absolutely. So it's a convex program.
Yeah, perfect.
Absolutely. So you need to solve convex programs. That's also, computationally, you'd be worried about this thing. Okay. Actually, computationally, I didn't even talk about how would you compute the median of a distribution. What's the dumbest algorithm you would think, computing the median of a distribution? Anything, dumb algorithms are fine. I love them. They get us started, right? I mean, this is one of the sort of problem-solving tricks I learned when I first taught an undergrad class. It's one of these things where you don't articulate it. Bracketing. Give a crappy algorithm. Give a crappy lower bound. It's fine. But now you have two things, you can push them together, closer to each other. So what's an algorithm? This is the first algorithm you think of. Now I put the pressure on you, so it's difficult to say something, right? But okay, so here's an algorithm. Just sample from this distribution a whole bunch of times and take the median of the samples. Okay. So, sample from this distribution, take the median of the samples. It might be some estimate of the. Okay. So one thing you can show is, well, this estimate, it's an unbiased estimator, and moreover, it actually will be close to the median with fairly high probability. Okay, so maybe I'll just write this down on the next slide. So sample xmax 1. So sample from everybody, and take the max. So that's a sample from xmax. Xmax 2, xmax let's say m, sample them m times, take the median of these things. Call this m. Okay, theorem. The probability that m, okay, so I want to say that the probability that x max is bigger than m and probability x max is less than m are both at most 1 plus epsilon, okay, lie in 1 plus minus epsilon times 1/2 if the number of samples m is bigger than, so the probability of that is bigger than 1 minus delta, something like this. Basically, take a whole bunch of samples and take the median of those, and that is going to be almost median. This is our distribution. This is our median. And I'm saying that this part has, 1 minus epsilon times half probability. And this part has 1 minus epsilon times half probability. And then this sample will lie in this region. Okay. Long story short, sample a bunch of times the x max and take the median of those guys. It's a pretty good median, approximate median. And then the rest of the proof goes through.
Anupam, can I ask another question? Sorry.
Yeah.
So in this algorithm, you showed this factor of 4, while the first one you showed a factor of 2, right?
Good.
So is there any lower, like how tight is how good is the lower bound or the upper bound in this case?
So this algorithm actually, instead of always choosing a fixed probability 1/2 of rejection, you can choose a varying probability of rejection and get, tighten up this bound. But, the proof gets just messy. It's we don't want to go there.
Okay, thanks.
Sorry, Anupam. I'm getting, maybe I'm getting
No,
confused
please.
too, but okay. So suppose one of the random variables that you have is just deterministic and the value is extremely high. Okay?
Absolutely.
So then you're completely losing that information. I mean, you know what the answer will be, but then you're settling for a much smaller value, right?
Good, because you're saying, so why would I be settling for a much smaller? So in that case, x max is always going to be that guy.
Yeah.
And then
and you know it will appear, so just wait a good sample.
Yeah. So in that case, by the way, Marcus, notice that this sample will be that high value. So I should clarify. X max 1 is sample from all these guys and take the max of them, and that's your first sample. This object requires n samples, 1 from each variable.
Yes, but even the median will not be estimated, and the median could be much smaller, right?
So if x max is a deterministic quantity, then its median is that value itself.
Let's discuss it afterwards.
Yeah. So no, I'm clearly sort of doing something silly that I'm losing you. So,
Anupam?
Yeah.
The whole point is that we don't know the order that the items arrive, right?
Good. So in this case, let's, the algorithms that I gave you, they kind of, I was assuming that we know the order in which the items arrive.
But why I don't use dynamic programming in that case, for example?
Good.
To solve it.
Good. That's an excellent point. Why don't I use dynamic programming? And then I can actually figure out that's the optimal algorithm, right?
Mm-hmm.
Because this is just a Markov decision process. Just to throw out a fancy word, if ignore what I said. Okay, good. So really, the issue is this generalization business, and that I want to generalize it to more settings. But let me answer your question in one more way, and maybe I'll just go to the next slide. And let me answer the question by giving you a third algorithm, which I'm not going to derive in full glory, but I'll give you a sense of this algorithm. Okay. One thing I assumed was I knew the distributions for both the proofs. Well, okay. Suppose I don't know the distributions. Or okay. So if I don't know the distributions, life gets tricky, right? So let me say the following. I am allowed one sample from the distributions. So I'm going to get values x1, x2, up to xn. This is the real thing. This is the real sequence. Suppose I don't really know the distribution, but I'm allowed one sample. From the same distribution, independent of x1, x2, xn. What can I do now?
You do know the distributions though, right?
So earlier I was saying I knew the distributions. Now I say my only access to the distribution is via these samples. So I can use, there's this black box that I have for each of these distributions. I can press a button, it'll give me S1, and then it'll destruct whatever.
But can an adversary maybe, like it sounds maybe too adversarial because are these IID or not?
These are not IID.
Okay, so maybe somebody can put the best at the end and
they can do whatever. They can do some crazy stuff, right?
Okay.
Good. That's exactly the issue. And now I can't do this dynamic programming. I can't solve this convex program. So what's a reasonable algorithm? I mean, there's many reasonable algorithms one can come up with. Here is one algorithm, which is just says, look at, let's set tau to be the max of the samples. My temptation was max of the samples divided by 2 or something like this. But in this case, the proof says max of the samples. Okay. And so the algorithm is take one sample each. Say this is S1, S2 up to Sn. Set tau to be the max over Si and pick first item that is bigger than tau. This algorithm has the advantage, so it has the sample complexity advantage. It's got amazing sample complexity. And the theorem says, this is a proof due to Rubinstein, I think Wong, and Weinberg. Let me just make sure that I am getting the names right. I always feel bad when okay. Yeah. this algorithm gets value at least half of opt again. Okay. So instead of proving this algorithm correct, which requires just a little bit of calculation, let me show you a related problem and a related solution. Okay. By the way, this algorithm, I mean, it makes sense, right? It's almost the sort of simplest algorithm you can think of. So let me show you a related algorithm. I'm switching gears ever so slightly. So here is a problem, and actually I'm switching gears because this is a sort of also self-interest, right? This is an older result of mine that once I saw this new proof, I was like, wow, these guys are really smart. But it reminded me of this old proof, so I want to show you this old proof in a different context. So this is Onlinesteiner tree, let's say. It's not important what the problem. Okay, so what's the problem? I give you a metric space, and I give you requests. So I give you a point, then I give you another point. So this is vector one, vertex one. Then if I give you vertex two, you have to connect it to vertex one, let's say. And I give you vertex three. You have to maintain a connected graph at all times. So you have to add an edge either this way or that way, whichever way you want to add. But you want to always maintain a connected graph. So in this case, the answer is clear, right? What should you do? You should connect it to the closest guy. Sorry, you should connect it to this closest guy. Now comes V4, and you can connect it to the closest guy you've seen so far. Okay. So vertex comes, you need to maintain a connected graph. So you always kind of greedily connect it to the closest guy you've seen so far. And you ask yourself, if I had given you the vertices V1, V2 up to Vn up front, what would you have done? To maintain the smallest graph, you would have computed the MST, right? Minimum spanning tree. But instead, you got things online. So it might cost you a lot more. And you want to figure out how different are these two things. So let me give you an example. The first vertex is this one. The second vertex comes here. Okay. Now, so actually, let me give you a graph, and let me show you. Okay, so the first vertex was this. The second vertex came here. How are you going to connect it? Everything looks the same, so maybe you chose this path. The next vertex I'll give you is I'll give you this vertex. And now you're thinking, look, I should have chosen the north route instead of the south route. But it's too late. You have to make these decisions up front. So you say, okay, well, I'm going to connect these guys up like this. But then I'll tell you, no. I'm going to give you these two vertices. So you'll connect up things like this, let's say. And in hindsight, what you should have done is you should have chosen this path. Okay. So in the online setting, because you don't see the future, you might get messed up. And it's natural, right? But this is a very quantifiable proof, or this is a very quantifiable example, a quantifiable setting. Okay, good. So in fact, I'll just mention the results. These are sort of classic results. So theorem, this example can show where online versus opt is bigger than omega of log n, and the greedy ensures that online versus opt is no bigger than log n. Okay, this second part I haven't proved, but catch me sometime and I'll tell you the proof. Okay. So let me so this is the Onlinesteiner tree problem. Let me give you a so suppose V1, V2 up to Vn were draws from were random draws, were drawn from a distribution. So our whole focus was stochastic, right? So now suppose I tell you that V1 is going to be drawn from a distribution, and I tell you the distribution. V2 is going to be drawn from an independent distribution, I'll tell you the distribution, and so on and so forth. So each of these are random vertices in the graph. V1 is, whatever. Okay. So here's an algorithm for Steiner tree. So for Onlinesteiner, okay. Take samples. Take one sample, S1, from the distribution for V1. Take a sample S2 of the distribution from V2. Take a sample Sn. Okay. So you took these samples, and maybe these samples I'll write in red. Okay. Build a spanning tree. Build a minimum spanning tree on these samples. Build MST on the samples. Okay. Now, when you see the vertex Vi, connect greedily. So now the actual request will come. This is kind of like preparation. I don't know what's going to come tomorrow. I know the distribution, so take one sample each and build a tree. And now when a request comes, find the closest point and connect it. And next request comes, find the closest point connected. Next request comes, find the closest point connected. Okay. Claim. Expected cost of the algorithm is at most maybe 4 times, something like that. Expected optimum. What's the proof? I don't even know if I need 4, but let's do that. What's the proof? So first, I built an MST on the samples. But this is the same distribution that the actual guys are going to come from, right? So this guy, the expected tree here is at most expected opt, because I'm building the optimal tree on the samples. Good. Good. Now let's look at these augmentations, these black augmentations that I'm doing. The expected augmentations are sum over I, the expected distance of Vi from the previous guys. Okay. Is the expected distance So let me just look at one of these terms. Is the distance of Vi from, let's say, Sj, j not equal to I. The distance of Vi from all the sample points is at most the distance of Vi from all the sample points except the Sj's. The Si. But Vi is drawn from the same distribution as Si. So this is equal to the expected distance of Si from all the Sj's, j not equal to I. Okay. So what have I done? I'm saying look at Si. And I'm looking at the distance from Si to its closest other sample point. I mean, these distances sum up to at most the MST distance. So this sum, therefore, is at most the sum of d Si Sj j not equal to I is at most, well, actually it's at most twice the MST distance. The twice you might, twice is a boundary case. It's like if you have two vertices, then I is looking at its closest guy, j is looking at its closest guy, so you might count this edge twice. There's some corner case out here. But the important thing was these were just like samples from the same distribution. So the beauty of these algorithms, and I'm way over time. So the beauty of these algorithms is just the amount of sampling they're using is very little. So question, let me go back to, the proof here is a little more, you have to do a little more calculation, but the answers are very similar. They'll use the fact that Xi and Si are drawn from the same distribution. So at some point they'll say, oh, instead of Xi, I could have chosen Si instead. The proof is in the notes. It's like a very short one-page proof. Hopefully you'll understand it. Yeah.
Just a quick question.
Please.
So it seems like having just one sample from each distribution and knowing the distribution itself have the same power in the way like you get the same.
Probably you can, again, it really comes down to the kind of results you're proving. If you're proving these kind of worst case results, it seems like they have the same power. But if you actually want to use something about the distribution a little more, probably you can squeeze more about this distribution by looking at it, right? So it's it's really in the theorem you want to prove. As far as I know, if you guys want to sort of extend this, I don't know if there are similar simple proofs, like one sample proofs for like k items for matroids. These would be very nice to be able to prove, like one sample bounds. I think there are like constant sample bounds known, and the proofs then go via other methods, but sort of can we give the right proof for these algorithms? For these one sample algorithms, I don't quite know. So that would be a sort of a nice direction to go in.
Anupam, can I ask a question?
Please.
So in the Steiner tree problem, is there anything better that you can prove by having more samples? So is there like a trade-off that maybe you can prove that more samples give you some better bound and this degrades the number of samples?
So short answer, Jose, I don't quite know. I don't know. Yeah.
All right. Thanks.
Yeah. No, it would be nice to actually understand. This seems like a very natural thing, right? We should be able to say, well, using one sample, we can get something. And as we get more and more samples, we can quantify the advantage that we are getting. And these are the questions you guys are, trying to get towards. And I think this is very, very nice, very natural direction. And maybe we might need to go beyond the worst case out here. We might need to say, look, we'll make some assumptions and then we'll prove the results.
Oh, okay.
Good.
Anupam?
Please.
It seems that at least in the Prophet problem, you always compare yourself against the optimal offline solution. But what about, for example, like in the previous lectures about optimal adaptive solutions? Like, are there results in that area?
So the optimal adaptive solution for the single item case, as you said, the dynamic program will give you the optimal adaptive solution. For more general cases, I do not know of results which are against the optimal adaptive.
Answering the questions, the question you just posted for K uniform matroid, there is an algorithm that uses one sample from each distribution and gets 1 minus something that tends to 0 with K.
Oh, I see. Okay, so then
this is a paper by
clarifying that. So is it by the same guys? Is it by?
So not Wang, but Asar.
Okay, got it. So it's the older paper of.
Yes.
So is it the other Kleinberg-Weinberg paper?
Yes, that one.
Okay, so I should take that back.
But for matroids, I think it's not.
Because I seem to remember they were using like a constant number of samples or something like this.
I think they use one from each in a cyclone. Right?
I see. Okay.
Maybe there is something for matroids where they use more samples.
It's
I'm not sure, but for K uniform they use one. Yeah.
Okay, cool. So they give this for K uniform. Okay, so thank you, Andres. It's
Okay, so we've reached the end of.
We've reached lunchtime, guys.
Yeah, it's been beautiful. Thanks again for the wonderful set of lectures, and please take a moment to open your mics and let's applaud Anupam for this great lectures.
Yeah.
Thank you, guys. It's been great fun, and hopefully we'll do this again sometime.
That's great.